Our next speaker is also from TU Berlin. Well, he's at TU Berlin for way longer than I am. Is Hendrik Meyer.
Okay, yeah, I'll be talking about a practical algorithm for weighted k-hulls. And after the previous talk, you will hopefully have understood what a convex hull is. But in our paper, we are going to talk, or in this talk, we are going to talk about k-hulls, because they are a generalization of the convex hull. And actually, if we take the zero hull, so we choose this parameter k as 0, this is identical to the k-hull. And this is also why we are going to talk about the convex hull first. And after we did this, we will talk about our contributions on how to extend the k-hull to 3D and how to apply this to point clouds with confidence values that might be part of your pipeline. So, okay, we start with the convex hull, and we say we have a point cloud, and we also assume general position. So no 3 points should be collinear in 2D. We say the convex hull is the smallest convex set that contains all of the points. As before, we say, or we define half spaces that separate space into an interior and an exterior, and especially for the convex hull, we are interested in all the half spaces that have 0 points in the exterior and are defined by exactly 2 points of a point cloud. And in the end, we can compute the intersection of the interior space of these half spaces to get the convex hull. In order to compute the convex hull, we take any half space that we can find, and we start rotating around this blue pivot point in a counterclockwise fashion. We find a new point and connect these 2 points. This will give us the next half space, and this is a simple step. We can continue until we are back at the original point. And in the end, we can use these half spaces for the intersection. And this is all I'm going to say about the convex hull construction, because now we want to talk about k-hulls. But before that, we also want to know why are we interested in k-hulls. For example, this ellipse is a convex shape, and I hope it's obvious that the convex hull of a convex shape is the shape itself. But if we now sample this shape and add some noise to it, we will get a convex hull that looks like this. And I think it's obvious to see that we don't want this because we know what the underlying shape is. So we would like to exclude some points from the convex hull. And this is where the k-hull comes in. We can already see in this example that it better approximates the underlying convex hull by exactly allowing some points to be outside of it. And this is something we now define. For the convex hull, we said 0 points in the exterior, but now we relax this property and say that there may be k points in the exterior. And this is all of the modification we need, because in the end, we can again take the intersection of these half spaces and say this is our hull. To compute this, the algorithm is also very similar to the convex hull, because we start with some half space that satisfies our constraints. For example, k equals 1, so there's 1 point in the exterior. And then we rotate around the blue pivot point, find the next point, and connect these two to get the next half space. We then continue this counterclockwise rotation around the newly found point, find a new point, create the half space, and so on. We continue this process until we have found all of them, and we've done 1 full rotation with our half space. This algorithm actually finds all of the half spaces we need because we do a continuous sweep over all possible orientations of half spaces, and we find the minimal one of excluding up to k points for each of the orientations. And in the end, we store only the ones that are defined by 2 of the points in our point cloud. This algorithm that I presented is already known since 1987, and it was proposed by Richard Cole, Micha Sharir, and Ji Yap. But there's one specific line in the paper that I would like to highlight here. In 3D, there is no obvious rotating plane algorithm generalizing the algorithm in 2D. However, we found that if we reinterpret this 2D algorithm in a specific way, it will allow us to do exactly this, a rotating plane algorithm. And so let's assume we have the following situation. We have a half space that has exactly k points in its exterior. In this case, k equals 2. In the following, we will call this a k divider because there are k points in the exterior. And if we now rotate around the pivot point, one of 2 things can happen. First of all, we find an interior point. And this is probably the standard case that everyone would expect. We start with k points in the exterior and we end with k points in the exterior. So the resulting new divider is therefore also, again, a k divider. So we start with a k divider, end with a k divider. Different side, but okay. But let's look at this second example, because now we have a k divider, 2 points are in the exterior, and now we rotate around the blue point. So the idea is the same, or the situation is basically the same. But now we find an exterior point. So suddenly this means the number of exterior points was reduced by 1. And since there's now 1 point missing, we will call this a k minus 1 divider. And generally speaking, this means that a rotation from a k divider can reduce the number of exterior points by 1 and at most 1. So now that we have these two types of dividers that can appear during our algorithm, we need some way to get back to k dividers because we are interested in those because we need them for the intersection. And we do this by choosing the rotation direction of these dividers. For a k divider, we rotate such that the non-pivot point of our divider moves into the interior, and for a k minus 1 divider, we rotate it into the exterior. And we can see in this case that the intermediate dividers we show here that will appear during the rotation will now always have k points in their exterior. And after we find the next point, the result can be either a k or k minus 1 divider again, depending on what type of point we found next. But we now have a way of handling k minus 1 dividers by choosing the rotation. And in 2D, this just works, but in 3D, we have to differentiate. Because in 3D, we now rotate, the dividers are now triangles instead of lines. So we have 3 points. And now, instead of rotating through the points, we rotate around the edges. Rotating around an edge, we will find a new point, and with a new point, we can define the next divider. And so far, this is still similar to the 2D case, but now we rotate, because we rotate around edges, this allows us to define a graph traversal of the dividers. We start at one triangle, and we rotate around each of its edges. This finds 3 new triangles, and we continue our traversal with the newly formed edges. And in this way, we can traverse the whole graph of dividers, and this will also find us all the k dividers. We stop traversing around an edge if the adjacent divider is already part of our graph. So in the end, we cover the whole graph, and yeah. And now we get to the point where we made this reinterpretation I mentioned earlier, because the same distinction between k and k minus 1 dividers can also be applied to 3D, because if we have a k divider, we choose the rotation such that the third point of the triangle becomes an interior point. And then there are again 2 possible outcomes. The next point we find is an interior point, so the resulting triangle is a k divider. And in this case, again, the points in the exterior have not changed at all. But we can also find an exterior point, which means the resulting triangle would be a k minus 1 divider. And now we need a way to handle the k minus 1 dividers. But here again, we choose the rotation such that the third point that is not part of the pivot edge becomes an exterior point, re-establishing k points in the exterior. And again, we can have 2 cases. First, the new point is an interior point, which means we have a k divider in the end, or the point is an exterior point, which means we have a k minus 1 divider. And with these 4 distinct cases of k and k minus 1 dividers, we can now traverse the graph and find all k dividers, but we will also traverse k minus 1 dividers in between. And the proof why this finds all the k divider is not as simple as for the 2D case, where we could say we check all possible orientations, but you can find it in our paper if you are interested in it. Okay, so this is all we need for the 3D algorithm on how to find the k dividers. But we also need to find this next point I've already talked about. And I've already only said given a rotation, we find the next point. But how is it defined? And we always mean the one that exhibits the smallest rotation from the original divider. And this is the same in 2D and in 3D. But this we don't always know which is the smallest one, and to do this we do a search over all points. We start with some random point and find a new divider. And this old divider together with the new divider spans this space of improvements, all of the dividers that lie in this space have a smaller rotation to be reached. So in the end, we iterate over all points, and every time we find a new divider, we replace the current point and continue until we've checked all of the points. In the end, we have the one that has the smallest rotation. So I always say we want to find the one with the smallest rotation, but we don't actually need to compute the rotation. But the two dividers we now have separate our space into 4 distinct quadrants. And we can easily test in which of the quadrants a new point falls by testing if it's in the respective interior or exterior of the two dividers. And then, in the end, we can say 2 of these 4 quadrants would be an improvement and simply replace the point if it falls inside. And we test for this interiorness by using predicates, because they return either a positive or a negative sign depending on whether the points are in the interior or the exterior. But the problem is that for collinear points, predicates can be inexact as we compute them using floating point values. So what can solve this are exact predicates because they return 0 in the case of collinear points and not just some random value based on floating point imprecision. However, in our algorithm, it is not clear how to handle these collinear or in 3D coplanar points, which is why we assumed general position before. But usually if you have some point clouds, they are not always in general position. For example, if you think about the Thingy 10K data set. And to solve this, we use symbolic perturbation, a technique that was introduced by Edelbrunner, because these predicates consistently return a non-zero value even in the presence of collinear points. And with this modification, we can now assume general position and can robustly handle all point clouds. So I've talked about how we can make this robust, but we also would like to do this fast, because currently the search has linear complexity as we need to test every point if it's an improvement. We do this by using axis-aligned bounding boxes, which help us to group points together. And in the end, we can always check if a bounding box intersects the space of smaller rotations, and if it doesn't, none of its points would be an improvement. For example, we can ignore this one marked with an X. And we can organize bounding boxes in a hierarchical structures, allowing us to prune whole subtrees. So with this information on how to compute the K-Hull intersections, we take a look at some qualitative results. We take some point cloud and add noise to it. And on the left, you can see this point cloud we use, and on the right, you can see the original convex hull without the noise. And this is what we would like to get, because we know what the underlying shape is, we know, therefore, what the convex hull should look like, and this is what we want to get. But the problem is, for small k, and especially 0, as I've shown in the beginning, the k-hull grows larger than intended, since the outliers pull the faces outward. If we increase k, the k-hull shrinks back toward the true shape. In the top row, we can see that choosing k around 30 is best approximates the hull, but in the bottom row, k equals 20 is already a sweet spot, and going further would overshrink it. And this already shows that the choice of k is important. So we need a way to find k such that the hull is neither too big nor too small. And we do this, or we try to find this optimal value of k by looking at the average triangle area of the dividers we find during our algorithm. Because we found that the minimum of this metric often also coincides with the minimum of some surface distance. For example, the chamfer distance between the K-hull and the underlying convex hull. Unfortunately, this does require us to compute all dividers for all the K values we want to test, making this kind of expensive. And this works best on the kind of noise we see here, this kind of speckle noise, where it is randomly surrounding this original shape. However, we found this to be often enough a good approximation. We also compare our method against the only available implementation that we found, which computes the Tucky depth, a concept that is closely related to our K-hull. And in these plots, each of the points is a mesh from the Thingy10K dataset, plotted as elapsed time over the number of points in the point cloud. And we're almost always faster for a small k, and with large k, our asymptotic complexity still beats the Tucky version for large points clouds. So, yay for us. The comparison method is also not robust to coplanar points, which we solved using the symbolic perturbation predicates, and this would still increase their runtime to handle this. So the results are currently not even correct in some configurations. Lastly, we want to talk about point clouds that have confidence values, because this is already often part of your processing pipeline. And in this example, we have the seal mesh, and we add some noise to it and have a confidence value for each point, how likely it is to be part of the surface. So how do we add this to our algorithm? And we can do this in the following way, because we previously always defined the dividers to have k points in their exterior. But we can also redefine this by assigning a weight of 1 to each of the points. We can say that the sum over the exterior points should be smaller than or equal to k. And now that I already said that we have weights per point that are 1, we can also replace them by some positive scalar value. And then we get a new definition of these half spaces we want to find. This redefinition requires a modification of the way we find the next half space, but the graph traversal itself stays the same. And in the end, we can take a look at these at the point cloud I've previously shown. So on the left, we have the convex hull of the underlying shape. And we can already see that the weighted K-hull better approximates the convex hull, especially on the large flat areas at the back or at the front and at the top. We can see that it really well reconstructs this, while the K-hull on the right fits the convex hull less tightly, having more rounded out features. And we can also see this in the following plots, because looking at the upper plot, we can see that the weighted K-hull is actually able to approximate the convex hull better, while also keeping the total number of excluded points smaller, which is a very interesting fact, as it shows that using weights we can exclude less points and create better approximations. And this effect is also visual in the bottom plot, because computing the optimal weighted K-hull takes only about 2 seconds, but for the regular K-hull it takes a lot longer. So far, the K-hull and its weighted extensions have found limited use in 3D applications, and we think this might be, on the one hand, due to limited awareness to its existence, and also a missing practical algorithm, which we have now provided. The algorithm is stable in the presence of coplanar points and faster than the current alternative we found. Also, the weighted K-hull extensions should also prove useful in the case of per point confidence values, which often are already part of your pipeline. Our implementation currently only works in 3D, but we are only limited by the robust predicates in higher dimension, especially in conjunction with the symbolic perturbation. And if we have an implementation for these, this algorithm should work in higher dimension. And yes, I will publish the code soon, so check out the link if you are interested in K-hulls, and thank you.
Questions? Questions? I'll start. So in your formulation, right, k has to be a constant integer for the entire space, right? But I can easily see situations where you even mentioned that sometimes you don't know what is the optimal k. And then also there could be situations where you want k to be 2 here, k to be 3 here, right? So in that situation, it seems like it might be related to the gamma hole that you mentioned.
So you mean this weighted version, this weighted KL? Because we can, in the end, we can exactly do this, like, if we know at some point we need only few points outside, but on another point there should be more, we can dynamically weight these points and get exactly this result of excluding more points on one side of the mesh and less on the other side, because the initial k-hull simply always says k points should be outside, but using these weights we could dynamically adapt.
All right. More questions? I mean, I'm also happy to ask more questions. Well, I guess, the reason why I ask about the k-hulls and, k being a constant is that it seems like the application at the current moment is you take a noisy point cloud and you want to compute a convex hull while being robust to the outliers, right? But again, right, the outlier distribution might not always be exactly k outliers on each phase of the k-hull, right?
Yeah, and I think this would be really a good way to use this weighted k-hulls. And this is probably also the case for why this works a lot better for the weighted k-hulls instead of the regular k-hull.
Great. It was not colluded Q&A. Okay, any more questions? If not, I guess our session concludes, and there is going to be city tour, and well, I think I can wait for the conference organizer to make the announcement. But give it another round of applause for Henry.